So I think it's time, so we're going to start. It gives me great pleasure to introduce our speaker. This the NITheCS Seminar, and the speaker is Professor Naresh Dadich. Naresh is a very experienced academic and researcher. He's been around for some time, which will become obvious when he stands up. And he was a long-standing professor in the Department of Mathematics, I believe it was, at the University of Pune. And then he joined a professor at UKZN in Pune. UKZN is the Inter-University Center for Astronomy and Astrophysics. It's a remarkable place to visit, where it encourages collaboration, physics, and it's a stunning architecture. He then went on to become a director of IUCAA, and now he is emeritus, roles in emeritus positions there. He has had long-standing links with South Africa, particularly with the old University of Natal, and now the University of KwaZulu-Natal. And he's a regular visitor, collaborator of a number of people, and the research is something that has been going on over the years. Two things I should mention about him that most people may not be aware is that India now is a partner to astronomy projects in South Africa. One is SALT, the Southern African Large Telescope. The other is SCAR, square kilometer array. And what most people don't know is that he was a driving force behind this to get the Indian government involved, and now they are the senior partners. We recently had the Centuries and Dimensions workshop, which was held in Digital Peak, and he was a plenary speaker and gave 4 talks theme relating to physics underlying gravity. And as you'll soon discover, he has a unique lecturing style. So over to you.
Thank you, Sudhir. It was always a pleasure to be here. There is one little correction to what Sudhir said. The SALT years that was became the member of the SALT Consortium, of the director, but not SPA. SPA is a much more which is actually the driving forces of neighbor, the NCR, National Center for. Okay, I see the most of the crowd that were there is better than clear, but because you are wondering all this, what all of you already know. Let me try to give you this. The basic thing is the same what I spoke there, but has slightly more a different perspective. So our whole idea was this. That what is the end state of a gravitational collapse? So the general thing all textbooks tell you is that yes, you have as the matter collapses, then other matter fields come into picture. And you ask the question that this is so what is it that opposes the collapse? So generally what we say, if you are talking of a fluid, then it's the pressure gradient which opposes gravitational collapse. Now we say, okay, if the mass of the body is large enough, the pressure gradient is sustaining, counter it. So it further goes on collapse. Then kicks in what Chandrasekhar did in early 30s, that bring in the quantum mechanics and to see what you call the electron degeneracy, that you compress something to distinct that electrons can no longer remain in the orbits. And that gave that famous Chandrasekhar March limit for a white dwarf, 1.4 solar mass. And then the story comes here. Once you have the electron degeneracy, then the next thing comes over. Then you have electrons are all evaporated, so you are left with a nucleus. Neutrons. What we call a neutron star. The neutron star, the most effective driving force there is with the Yang-Mills or the nuclear force. And you again ask the same question that if the gravity still wins over all this, then there will occur the neutron degeneration. And then there is nothing left, and it should start collapsing down all the way. So this was the thing which was triggered by Chandrasekhar's work. And as I said earlier, that when he presented this work in the Royal Society, Eddington, though he was one of his greatest friends and admirer, opposed this thing very vehemently, but not for any justifiable physical reason, but more for a philosophical reason to say there must exist something in nature that such kind of a catastrophe doesn't have. It is one of the most unscientific arguments, if at all it can be called an argument. However, on the other hand, we may ask this question that is there any other equilibrium state possible which is not before it collapses to a black hole? So that's so as it you are when you are saying it collapsing, what you are saying is that the object becomes more and more compact, and the compactness we define as a mass to radius ratio. So you have a, so this is our compactness, M over R, to the given radius, how much mass it can include. So now, and of course, naturally we would ask that the limit of the collapse should give me the limiting compactness, the most compact. So the one we all say the limiting for the most compact object in general relativity is a black hole. So now what do we get? So you have a black hole which has the compactness and over R R equal to Q1 in the black hole radius. This is what I do. And how do I define a black hole? So you have a geometric definition of a black hole telling us that if I have a time-like killing vector, when it turns null, that gives you the, in a more common sense language, that the massive particle has a time-like velocity. Under what conditions, when does it becomes, its whole velocity becomes null. And that happens at this radius r equal to 51. And the idea, of course, the Schwarzschild exterior solution is that geometry defined describing such an isolated object. However, in this definition, it's very beautiful and nice geometry, but it is physically not very enlightening. Because physically, what I really like to see that this is the most compact equilibrium state. If I have, then I must have balance between the forces, in the two forces, one which is opposing the collapse, or one which is favoring the collapse. So it should be something to do the gravity and the agent which is opposing it. So we ought to get such a balance of problem. And now if you want to have this compactness to be limiting, by limiting I mean that it is free of any matter conditionality. That you don't say that this under this equation of state in this quantum, so it is totally free of any matter condition. So like equation of state or whatever. So under this thing, now this would mean this will be possible that this equilibrium, limiting equilibrium should be completely determined by the gravity and the three particles in motion. So you have three particles which only interact through gravity, no other interaction. All other interactions have been 1 over. And then you will get a limit, you will get a compactness limit, which will be free of any matter condition. No matter construction is involved. So that is what we would like to see. Which essentially would mean is that it is a gravity versus the motion. That's the picture which like. Now, in here, let me get back to say, what do I have? So let's say that if I have some object of radius r. Yes.
So when you say motion, it is like kinematics.
Dynamics. Particular motion in general, what
Because then it adds to the US of the matter, which is
what that is?
that adds to the US of the matter. Yes. You first said that you
He means massless particle.
No, but why you tell us I have a, so the picture which you I have three particles, so for example, yeah, three particles, pressureless, no pressure. There is no interaction between yeah. So no, you can no. If you really want to think of, this is what Einstein had done. This is a in a rough way. This is a picture of what you call Einstein cluster. That you have a particles which are moving in opposite directions circularly. So to keep the equal number of particles going one way, equal number of way other way. So total angular momentum is 0, and this is kept by equilibrium by the gravitational effect. So this is a one picture of it. And since you already say so, I must say that like the Eddington, Einstein also did something this, which was not very nice. And this all was done before the before 1960s. Einstein died in 1955. The scientists are equal to 2m surface of the special solution was people who did not know what. So it all started from things, oh, matter can never compress to such a small radius, like saying that the entire sun being compressed down to 3 kilometers. And so Einstein, on the other hand, constructed this model that you could have a model of this, what we call the revolving particles, and which will not have whose radius will be greater than 2m. And so you're saying that, yes, maybe the matter does not collapse down to such a, but by the 1960s, the Crystal and others came out, and they did prove that, yes, R equal to QM is not that way physical thing. It is a coordinate singularity. You can construct a coordinates value for R greater than QM and less than QM and maximum fine. However, R equal to QM has a very remarkable, interesting physical property. And that the most remarkable physical property was that there's a time-like killing vector turning null, or which means nothing can remain steady. So that so, but however, like the Eddington, even the we will see that Einstein's this picture was also not very good. So here we are asking the question. So now I'm throwing out everything else, and now asking the question is that if I am only concerned about the gravity in the ocean, and which, as clearly speaking, we know classically, this kind of thing, this is what we do in linear. At the virial equilibrium, you have your average kinetic energy is equal to half of the potential energy if your system is bounded enough. When you are taking average, you are taking average all the time. So this is so that is where it's gravity and the motion, these are they balance each other. Now we want to go a little beyond. And as a matter of fact, what I want to see is virial theorem for general relativity. So here what you had So classically, you have the kinetic energy, potential energy. One question you say, okay, let us try to define this kinetic energy, potential energy, general energy. The problem is, in GR, you cannot separate kinetic energy and potential. So if you look at your key particle Lagrangian, what do you write? You write the norm of the formulas is GAB, UA, UB. That potential energy is sitting in GAB. I don't add added a potential separately is GAB, which gives you this. And GAB, UAB is also a kinetic energy. So that means that this cannot be directly you cannot take. But let us do something more rudimentary. I say that, okay, so that let's say the energy which is lying outside the radius R, let me call it R, and this energy is the gravitational energy, which extends from R to infinity. Then I will say, what will be the energy inside? Now, at infinity, the mass, total mass, is the mass m. You start with, which is when the body is infinitely dispersed, and it is only bare enough to sum over it. This must be possible. You at infinity, you start with the mass m, and as it collapses under its own gravity, it picks up the gravitational energy, which lies from R to infinity. So naturally, the energy inside the radius R, what you started with m, and this is what is lying outside, n minus p. This is the energy that is. Now, this gives us three possibilities of equilibrium states. So one was this, which one we have already taken into account. One, this meant that E out, it is same as Vt equal to 0 at R equal to infinity, R tending to infinity, and the entire energy is in m. That is what you. Now, other possibilities. So here we took that gravitation E out is 0. We can take the something which is the dual of this, and demanding that E in to be 0. E in is minus EG. This gives me m equal to EG. So this is another equilibrium state we have when the mass or the non-gravitational energy is equal to the gravitational. And in this case, like here, the entire energy was in, so the entire energy will be out. Only the EG equal to m. So in interior. And third possibility is, of course, where you can say the E in equal to E out, which means M minus EG equal to EG, giving us EG equal to half. So the first thing to note in this picture that these are the only two equilibrium states I have. So when I have a distribution which is free of any matter conditions and only interaction with by gravity, then we are led to only these two. These are the only two equilibrium conditions here, and nothing else. Now, this all will make sense if I'm able to compute the EG, the gravitational energy. So that is where the crux of the matter is, that the gravitational energy is difficult to compute, not only because this is it is a firstly, energy by itself is a very ill-defined concept in general relativity. Then, no. And more so the gravitational energy. That is why we have many gravitational descriptions for gravitational energy. But however, one may say that in a given particular physical situation, we have some good description. And the goodness of the description is the test that it gives me the first approximation the result I expect from the Newtonian gravity. And secondly, it fits into the overall picture of physical picture. Now, how do I go up?
It means giving a
Do this. So now we want to compute gravitational energy via the prescription between Brown and York. And that prescription was that energy contained inside the radius is given by 1/8 pi k minus k naught q dx. So what you have a picture here is this. I'm like 1 plus 2 surface. You have the two surfaces having the extreme equal to the k. This is your reference surface having the extreme equal to k naught. And this is from the time direction. So, and the Q is the metric of the two spheres. So that the Q is the determinant of the two metrics. This if you integrate, so this is exactly the same thing we are talking about. That infinity, the mass is done as it collapses, it picks up the gravitational energy. This is the total energy contained inside the radiation. Now, if the system, our object is is isolated so that if the geometry is asymptotically flat, so the K naught will be the radius of the two-sphere plane of the whole space. And if you evaluate this for the Schwarzschild solution, then this has a close relation. Now we do this, that the EG, as I have said, I define the EG is defined by the ER minus M, that gives me R minus R squared minus 2R minus M. Once I have an expression for the gravitational energy, then I can see all my those three conditions. So, our three, one is a trivial one, that R equal to infinity, mass is the internal gravitational energy is zero, the entire energy mass. So the two of this, the equilibrium 2B, which was the n equals to Eg, so this m equal to Eg means putting this equal to m, immediately you see it leads to R equal to 2m. And R equal to 2m is, that's what defines the black hole. It defines the black hole. There's a formula. This, so this is the first time you define the black hole as an equilibrium condition between the gravitational energy and non-gravitational. And that was done in 97, I think, somewhere. So this okay. So this is where the equipartition of the gravitational and non-gravitational energy define the black hole. And thus, you wrote this. The next approach comes in, the next thing that comes in is that where Eg equal to half it. That process will give you M over R. Now this I would say, this is what we call the black hole. This defines the Buchdahl star. And let's now come to the Buchdahl star of other than world.
We'll use slowly.
Okay. So now let's ask to come to get back to this question. The 1959 Buchdahl asked this question: that if I have a fluid star, how compact could it be? And for this, he asked that the density must be non-increasing from the center. And so, pressure is isotropic. And then matching with vacuum. Under this condition, you got this famous Buchdahl bound and M over R less than equal to 4 by 9. So that's the yeah. Then there is a lot of literature about it, but that's not our concern at the moment. What we then, what will happen is, so this is, I think, 2017 or 18, I don't know, one of these. Yes. When I was visiting this place, Ritu Purnam Goswami came to me and said that for F of R gravity, they have found a corresponding Buchdahl bound. And then when I was thinking about it, then it just occurred to me that what I did to define a black hole, that the gravitational energy equal to the mass, define the black hole. Let us try, so I know this M over R or 4 by 9. So let me write gravitational energy minus this equal to some alpha times M to tell you this. And demand that M over R is 4 by 9.
Same bound works in F of R as well. 4 by 9.
Oh, no,
It changes.
It's
some additional
That depends on some counting parameters.
Of course, it depends on the function f of the So the then, and then it turned out the stand for that is turned out to be in terms of the gravitational energy, in the non-gravitational energy, the bound could be written as the gravitational energy is less than equal to half times. So that's also, I don't have to be, this is some point here. Yes.
Naresh, just taking F of R as just one example of an extension of Buchdahl derivation. Which direction the bound goes? I mean, goes to 4. The extra F of R terms, it increases that number 4 by 9 or decreases? Does it define the?
I think, well, I'm not a fan of a bar, but my general theory is anything modification will increase the bound. Will decrease the bound. So that Einstein will be the most complex. That's I think between 1, 0. Then we can, you can, once, sorry, no, this is where I told, define that when this limit is saturated, all the other results. And over. Defines the Buchdahl star when the limit is saturated. So now you have these two objects corresponding to these two equilibrium states where the gravitational energy is equal to the mass, then it is a black hole. And when gravitational energy is half of the mass, then it is a Buchdahl star. And these are the only two states available to us. And this is what I call the relativistic virial theorem. So the relativistic virial theorem has one distinctive feature that it also determines the compactness. The Newtonian virial theorem, you can have a virial equilibrium with the arbitrary compactness. Here, the compactness is, and the reason for that is because here everything is in terms of the gravitational energy in the mass. Whereas the Newtonian, which are related to each other, because the gravitational energy is given in terms of m and r, and that you want to relate it to m. So you will get some relation between m and r. Whereas the Newtonian case, kinetic energy and the potential energy is more direct relations. And so you could have a so that's your and this is when we something deep. This is how I define the Buchdahl star is a virial star, a virial or virial fluid. So that's so here now. So now the picture is you look at the question we have. This triggered us to give that can we have a so for first thing which came about was that we could translate it into a geometric virial theorem where the kinetic energy and the potential energy are in terms of the geometric scalars of in the 1+1+2 formalism with the 3, 2 and the Sierra. So that but now let's come to the next question because more interesting. 5 minutes. Oh, good. Good. I think maybe this all is very soon. I can just give you the. So now we should really look at the gravitational collapse. So you have a fluid which is collapsing in the. And now what we are saying is that the ultimate equilibrium states available to us is the M over R equal to 4/9, defining a Buchdahl star, and M over R equal to half, defining a black hole. So first thing is the fluid which you have, it should become a virial distribution. for this to be, the virial theorem to be applicable. So that is to say, fluid should split up into the free particles. So you will have a virialization. So the matter undergoes the virialization by which it is becoming splitting into the free elements. And that happens due to the tidal forces produced by the curvature. The tidal force and break the fluid that produces the heat. And so this heat radiates out as a weather radiation from the boundary of the crevices. So one general statement we have is that the gravitational collapse, as it proceeds, it has to first radiate out heat as a weather radiation. Now this thing we had earlier with Ritu and I had looked at, that if I have an accreting black hole, I have a black hole on which the matter is accreting, and there again we had argued that the accreting matter, which is in general is time-like fluid, as it approaches the horizon, it should become null. So it should undergo a transition from the time-like to null, and that transition also is done through the your tidal distortions giving rise to heat. So with that, in the case of a black hole, there is another problem. You have a Hawking radiation. Now the Hawking radiation, where does it originate from? So you wanted Hawking radiation to originate from as the from the near horizon, but as it accretes, horizon tends to become space-like. And from the space-like, anything emanating cannot reach out. Now, so the question that you ask is, okay, let us try to ask, how much energy do I need to keep that the horizon continues to remain null? Does not become space. The amount of energy needed, this is precisely the amount of energy which is radiated out of heat in the weather radiation. So that is how we say that accreting black hole has to first weather radiate so as to make Hawking radiation to come out. So that's the first picture we had here. Now here, these two equilibrium states, you can say one equilibrium state is for the massive particles, mass not equal to 0, that gives you the Buchdahl. The other equilibrium state is for the massless particles, that is what gives you the black hole. Now the question I'm saying is that ultimately we come to the question, so what is the end state of a gravitational collapse? Could it be a Buchdahl star or could it be a black hole? Now, the MOR 4/9 is reached earlier than the MOR is half. So first it will become a Buchdahl star. If the Buchdahl star is stable, then there is no scope for to go to the black hole. Now the critical thing depends on the stability of a Buchdahl star. Now I'm saying yes, in principle it looks like it has to be stable. Of course it has to be actually worked out and so on by the rigorous calculation. Because the equilibrium is defined by the mass and the gravitational energy. the mass produces gravitational energy is produced by the mass of the room. So the two are intimately related. When I am saying that when I perturb a system, whatever the perturbations are due to the mass, corresponding perturbations is automatically produced in the gravitational energy. And if they were earlier, initially they were in equilibrium, they will continue to be in equilibrium. So there is a conceptually that it is a. So now 1 minute to say that if in case gravitational energy, the Buchdahl star is end state, not a black hole. The first thing is many of the troubling questions like the quantum information paradox and or in even taking this in the for an external observer's frame, it takes infinite time to reach a black hole, all those sort of things evaporate away. Second question, it also answers one of another very important question. Because in this picture, then, there is no scope to produce a naked singularity. The naked singularity. So your cosmic censorship hypothesis all goes. All that what you do for black hole, you should now do to Buchdahl star. And as a matter of fact, it opens up a new avenue that all what we remarkable results in the phenomena we have obtained for Buchdahl for the black hole have all to be now translated to the Buchdahl star. And that would be the last point here. This was the gravitational collapse leading to the Buchdahl star. How about the cosmology? That's where I was asking this. See that Roy and Stanley, Roy Martins and Stanley Nell did this very beautiful piece of work that if you take the density distribution at present epoch and evolve it backwards in time, and then they showed that it really goes down to a black hole or to a horizon. It holds. Now, I think it will be most interesting thing to see in our picture of this thing, instead of the horizon, could it be an equivalent of a Buchdahl-like object? So could it, instead of a Big Bang origin of the thing, could it be an origin of a non-black hole, non-horizon object as from where the now this is the thing. I'm not as you all know, I don't do some calculation, but this is something that I have not even much thought about it, but it will be a very interesting thing to explore the same question for the cosmology. Thank you.
Thank you, Naresh.
Thank you. Comparing Buchdahl's theorem, how we derive what's got using energy and using philosophy, so spherical, sensory, gradient, negative, and it goes on the equation, and then compare it to Schwarzschild infinite, quantum density. In other words, equality is achieved. Schwarzschild.
Oh, sorry.
That's a necessary.
No, you can get the thing called from the source demanding that the pressure at the center will be final. But the Buchdahl derivation have not the constant density. You don't know. It may actually be only these three conditions you can do in general. We are done for the law of the density is decreasing from the center and the pressure is isotropic and matching to the exterior vacuum. Only under these three general conditions, not much of a differential equation being used. It's really what you go through is just looking at the matching condition and the so.
So what I'm saying is that Buchdahl star is a Schloss. Within the Buchdahl star, Schloss.
Yeah, so they're good question. So interestingly, Schwarzschild solution describes an object irrespective of whether it is a black hole or non-black. And this is very important. This is not the case for the Kerr solution. Kerr solution can only describe a black hole noted in general rotating object. So that so far as the exterior matter is concerned, whether it is a Buchdahl star or any other star, could be sun or anything of any area, this will be exteriorly described by this process.
Yeah, with those conditions that you got, is it possible that that carbon both by some other thing else?
Okay, so there have been some things by assuming different analytical results. This 4/9 would be for the pressure and isotropy in that one. There is quite a literature on that. But what has not been shown that a realistic for a realistic star, Buchdahl bound in the bounds. So the 78 group, although 22 established that in the very specialized conditions you might violate the Buchdahl bound, but like you see the physical physical conditions will demand the sound velocity should be less than light velocity. All the sort of thing put in these all physical parameters. Then it's the Buchdahl bound. So that's how. So if we can take Buchdahl star as a true astrological.
And the machines to play games Punch is available, please before Russia. And he welcomes, should I say, vigorous interactions. So let's thank Dadich again.
Never take everything what we say seriously.